Hello everyone. We're going to start our new series today, which is going to be on mechanical vibrations. So, a vibration is, anything that can move back and forth. So, if you've ever had a spring bobbing up and downwards, that's a vibration. Your hand moving back and forth is a vibration. It's just a repeated oscillating motion. Now, mechanical vibrations is a very complicated topic, and the math is going to be pretty complex because it's going to have to be, and you'll see why in either this video or the next. Now you'll see some of it at the end of this video. Well, since this video is going to be an introduction to vibrations, and we're also going to cover how to analyze springs. So due to the complicated nature of these videos will usually be a little bit longer than the thermodynamics series, especially once we get to the more in-depth problems. As a result, I'm going to be doing a topic in one video and then a problem in another video, so the videos are not like an hour long. So let's get into it. So when you're dealing with springs, everything can behave like a spring. If you know anything about materials, or if you don't, I'll give you a quick brief on it right now. So any type of material has a type of stress-strain curve, which is just stress is like a force per unit area, and strain is the change in length of a material over the original length of a material. Now, you don't really have to know fully what these are to understand vibrations. We'll be doing a materials series eventually, but you just have to know what stress and strain are by these definitions. So like if I had some material here and I stretch it out to here, this would be my delta L, this is my original L, my strain is my delta L over L. So these curves for a material usually go like this most of the time, or they have this general shape, and at this point is when the material will just break. So there are two regions for this material. There is the elastic deformation and the plastic deformation. Now, elastic deformation means that it's not permanent, so any change you put on the material, you can get back. And this is the region that we're going to be focusing on, because this region is where materials behave like your basic springs that you might see anywhere, really, in a car, in a small toy, in almost literally anything on your lamp. During this region is where it behaves like springs. And in this region, the elastic modulus, which is basically the slope of this curve, of this line here, gives you a specific, the elastic modulus tells you how much a material will move under a specific amount of stress based off of these material curves. And as a result, from this value, which is going to be a constant value, from this value you can determine the spring constant. And if you ever covered springs, like you have some wall, if you recall, and say I have a mass here, some value K, well, every material has some sort of spring constant, and this spring constant, K, constant K, is dependent upon, the material properties and the geometric properties of your object. So by material properties, I'm talking about your elastic modulus, which is used if you're compressing or pulling on a piece of material, or your shear modulus, which is G. This is E, by the way. And what the shear modulus is for when you're twisting material. Well, also when you're twisting material, there will be a certain amount of strain where the material won't break but can spring back if the stress is removed. So we'll cover a couple of some common equations real quick just to show you. So common equations. So we'll do a rod under compression and tension. So a rod under compression and tension means that I have this rod here and I'm applying some force outwards or inwards, but we're just going to say outwards because it doesn't really matter the direction, the formula is the same. And that rod has some length L and some cross-sectional area A. Well, the spring constant for this material is EA over L, where E is the elastic modulus of the material, which would be given to you, or you can just Google it, like the elastic modulus of steel, for example, or the elastic modulus of wood. A is the cross-sectional area of the rod, and L is the length of the rod. So if I have some sort of problem here, which you will in the future, heads up, and say I have a mass either vibrating up and down or left to right, by using this equation here, or similar equation, or another similar equation, because this would still be tension and compression, you can, actually no, I don't think you can use this equation. We'll get back to it again. But say I have some rod, the mass being pulled back and forth upon this rod here, I can approximate it as a simple spring problem, K, using this equation here. And actually, here we'll do a rod under torsion. So torsion just means I am twisting the rod. We'll say the rod has some diameter D, and again, a length L. Well, the equation for the spring constant for this type of rod is G pi D to the fourth over 32L, where D is the rod diameter, L is the rod length, and G is the shear modulus. Now, okay, hold on. Now this is the equation for a rod under tension if I'm just twisting it back and forth. It's like if you were to, for example, twist a pencil or a pen or anything, and then let go, even though it doesn't look like it moved, there was some vibrations there because you twist the material, it had some K value, it just had a very, very high K value. So there wasn't much movement, but it did happen. So the next thing we'll cover for this would be a helical spring. And you might recognize this as just the basic default spring. Got a spring on your desk? That's a helical spring. You got a spring in your lamp? That is a helical spring. You got a spring in your pencil, or pen, for example. That is a helical spring. So this is how you determine the K value, or the spring constant, for these springs. This is actually also how companies who are manufacturers, when they make those springs and they sell them to people, you can find the spring coefficient on the data sheet for that spring, and this is the equation they use to calculate that spring constant here. K is equal to G D to the fourth over 64 NR cubed, where D is the diameter of the rod, and when you have a spring, for example, going like that, that's a bad drawing, but you get my point. That diameter there of that rod is what I'm talking about. R is the radius of the helical spring. So like when you just have a spring on your desk, and if you were to just look down the tube of it and measure its diameter, that's how you find that radius. While d is the diameter of the rod of the material itself, r is the radius of the helix, which is the geometric shape. So don't get them confused. D is for the material diameter, r is for the geometric shape of the helix. And then n is the number of coils, where, for example, this has 3 coils, 1, 2, 3. And then g again is the shear modulus. Now, these are just 3 example equations to show you how the spring constant is determined from the material properties and from the geometric properties, which is why we had to quickly cover what an elastic modulus is, which is the slope of the material during the elastic region of your stress strain curve. And then the shear modulus is just the same thing as during the elastic region, however, of your torque strain curve. So if I had a graph here, some linear region here, this is how I calculate G. And so this shows us how it's related to our geometric and our material properties. So there's so many different types of equations you can use for each of these, since they vary from shape to shape, so we can't cover all of them because this video will take forever. So let's now go into the next part of our video for introduction to springs in series and parallel. Now, when you have a system and your system has multiple springs that are involved, you're going to want to simplify it down to where you're only having to deal with one spring, which is called, and you give that spring a key EQ, which stands for the equivalent spring constant. And the equivalent spring constant is just the combined spring constant for each individual springs, and springs will show up in series or parallel. So first we shall cover parallel. Well, parallel just simply means this: they are parallel to each other. So K1, K2. Now, how would I find the equivalent spring constant from a parallel? Well, spring constant is just the sum of the springs. So if I wanted to, this would then go into a thing like this. That's simple. Now if I were to do series, these springs are like this, where this is K1 and K2, and instead of just simply adding it, it's the inverse. So 1 over the equivalent spring constant is equal to 1 over K1 plus 1 over K2. And so you're going to have to do some math to solve it, and you get that K EQ is equal to K1 K2 over K1 plus K2. So now that that's done, why don't we determine the a quick example problem using what we've learned so far. So we have some cylinder here, cylinder 1, cylinder 2. We'll say this has some diameter D1, some length L1. This has some diameter D2, length L2. Well, we have a rod here, and let's say it's being twisted. So we're under torsion. I'll do this in a different color. Nope, they want that gone. So bam, bam. So it's being twisted. What is our KEQ is equal to what? Well, if we remember, since these are cylinders, we can transform these cylinders into a problem like this, because the springs are connected in series. And you can see that because they're just one, when one ends, one immediately starts series. So this would be K1, K2. If we go up to our previous equations up here, we can find the rod under tension equation right here. So we get that K1 is equal to G pi D1 to the fourth over 32 L1 okay, K2 is equal to G pi D2 to the fourth over 32 L2. So combine them. KEQ is equal to, we're going to use this equation up here, of K1, K2 over K1 plus K2, which is going to involve G pi D1 to the fourth over 32 L1 plus G pi D2 to the fourth over 32 L2 all over, nope, no plus, this is multiplying, all over G pi D1 to the fourth 32 L1 plus G pi D to the second over 32 L2. Well, G pi and this are in every single term, so they can cancel out. And you're going to be left with D1 to the fourth, D2 to the fourth over L2, L1, L2, all over D1 to the fourth plus D2 to the fourth. Oh, that did not add correctly. L2 D1 to the fourth plus L1 D2 to the fourth over L1 L2. Cancel out. You get that KEQ is equal to D1 to the fourth D2 to the fourth over L2 D1 to the fourth plus L1 D2 to the fourth. There you go. Quick example problem. Shows you how to do it. Now, we're going to get into the real example problem to determine again the spring constant equivalence. However, we're going to do it with a different type of problem and a common vibrations problem that you will come across. So this problem is this. So some pin, some rod here. I have a spring here and a spring here. We'll say they have equivalent spring constants. There's some force F being applied at the tip, and this is 2 inches, this is 5 inches, this is 6 inches. And find K equivalent. Okay, well, right now it's in equilibrium, so to find K equivalent, we need to know the forces acting on it. So we're going to do a tiny, almost insignificant displacement on the rod, just a little bit. And so if we were to do that, we draw the rod down here, exaggerated of course. Here's the initial position. You're going to have X value here, a Y value here, and a Z value here, some theta. This is 2 inches, this is 5 inches, and this is 6 inches. Now you might be asking, but John, we moved it. How you can't say they're at 2 inches anymore because as the rod moves, those positions lowered. And you are correct. However, we are doing just so small, almost imperceptible movement on the rod that it's as if each point barely moved at all. And we're doing this so we can create a mathematical expression to determine the relationship of this rod. So we're going to use the small angle approximation, and this z value here we can say is 2 theta, y is 5 theta, 6x is 6 theta. And we're doing this again, we're doing this again just because we're doing small angles, so we can assume that sine theta equals theta, and we're doing angles so imperceptibly small that we can use this approximation here for the heights and create a triangle. So what's first? Well, you're doing a physics problem, so you gotta always do the free body diagram. So here's a rod. You have a force F being applied at the tip, force back here at Ky, force going this way at Kz, and then our basic reaction forces that we have to throw in. Now, no matter which way I move the rod, the springs are always going to oppose the motion. So since I'm pushing the rod to the right, the springs got to push the rod left. So, and since we're doing such a small movement again, remember, it's really, really small, we can say that, well, since we barely moved it at all, we can approximate the sum of the moments as they're all in equilibrium, because the rod is not really going to vibrate, it's just barely moving. I can't hit that point home hard enough. You're going to use it a lot. It's going to come in real handy. So, write out the moment equations. Well, F is 6 inches from the base, which we're going to put right here. So 6F minus 5ky, where y is the distance it moved horizontally, and minus 2kz, z is the distance the bottom spring moved horizontally. So if we say that theta is equal to x over 6, well, then we get that y is equal to 5x over 6, and z is equal to 2x over 6, which is 1/3 x. Plug this in, we get 6f is equal to negative 5k times 5x over 6. Oh, no, plus, remember, subtracted it over, plus 2k times x over 3. Just add everything up. 6f is equal to 25kx over 6 plus 2/3 kx. Divide by 6, you get f is equal to 25 over 36 kx plus 2 over 9 kx, no, 1 over 9. 1 over 9 kx. Add the fraction together, you get f is equal to 29 over 36 kx. Okay, now remember, force of a spring is equal to the spring constant times the displaced distance x. Well, we have a displaced distance x up here because we moved the tip of the rod. So we have a force, we have a distance, so the equivalent spring constant must be 29 over 36k. So again, just to go through everything real quick, you can determine the spring constants of any material or anything whatsoever by analyzing the material properties itself and analyzing what the geometric shape of that material is. So we did some common base equations here using the elastic modulus and the shear modulus to show a rod in tension and compression and a rod being twisted or in torsion. as well as deriving the equation for how to find the spring constant of, well, a helical spring. We then did a quick analysis here on how to add springs in series and in parallel, and then we did a quick example combining adding springs and going off of our material properties up here. And then we just did a quick base problem to show you how you use springs in physics. So, and this was, by the way, a simple vibrations problem, which is why this video is already over 25 minutes long, which is why the problems are going to be in a separate video, because we're going to need to go on a more in-depth analysis to show everything. Mechanical vibrations is a very hard subject, and it's also very long. The problems can be very, very long. So, thank you very much for joining me today. If you found the video helpful, please leave a like, and feel free to subscribe. If you have any questions, please let me know in the comment section. Thank you very much.